Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking a bit more about regular expressions and properties that regular languages have. And if we have time, I'm going to start easing into some interesting properties that regular languages have that will ease us into discussion about if all languages are in fact regular or they're not. So we're going to talk about this today. So I thought I would give you some kind of algebraic rules here for regular expressions. Some of these I've used actually last lecture. Remember, I was doing the process of constructing a regular expression from a DFA. I used a bunch. I had this recurrence relation that I used to build the regular expression. I had this construction I built inductively. What I did is I did a bunch of simplifications. Some of these rules I'm going to give you here are actually going to be a little helpful for this process. So if you're staring at it and you're like, I don't know how to simplify that, some of these rules will help a little bit with this. There's obviously a little bit of insight when it comes to simplifying down regular expressions, because sometimes you see something and it looks absolutely redundant for what's written there. And that does happen. So I thought I would talk a little bit about some laws for regular expressions. So first, there are commutative laws for union. I think I accidentally called this associative the last few lectures back. It was an A versus the C. It's hopefully this is fine, but essentially you could, with union, the order for which I give them to doesn't matter. In this case, so notice I have L and M. That's no different than me writing M or L, or M plus L, however you want to say that. It's union. Distributive laws, so for example, if I give you L with M and N performed with a union, then I could distribute it over L with concatenation. And it works the other way around as well. For associative, if I parentheses around, say, two union operation like this, I can also associate it with the other pair. If they're just unions, three of them like this or more. Associative, what you would expect, it's just now it's concatenation. Notice the order for which the concatenations do occur. Notice here that the order is still M, N, and N. I didn't switch any around, it's just the parentheses changed. So just take note of that. The order does matter for a concatenation. This is not the same as union. Union, the order doesn't matter. Now, a couple that I've kind of alluded to, but I'm going to talk about a couple that specifically came up last time, is that for union, if I have the empty set, well, the expression for the empty set, or empty language, and I union it with a language, then I should just get the language itself. If you're not sure about this one, remember what the definition of each of these expressions is. This is just empty set. This is just some set of strings for the expression L. But what does that mean? If I take the union of an empty set and a set with a bunch of strings in it, then it means I should have a set with a bunch of strings, right? And for concatenation, if you have an epsilon getting concatenated with a regular expression that represents some language, L, then the epsilon gets absorbed into that. So it doesn't really matter if it's before or after. You notice that the epsilon doesn't matter. Why? Because remember, epsilon is the empty string. So if I take a nothing to a something, and I'm like, okay, well, that's a nothing. This is actually a whole language. Okay, I'm trying to get something here. Like, it doesn't do anything with this expression. So just be aware of that fact when it comes to epsilon. This is different than the next one I want to talk about, is so-called the annihilator. It's a fun word. The annihilator for concatenation. This is the one we seen last day, where I took the empty set and I tried to concatenate it with L. And I'm going to tell you that that's no different than me saying that L is concatenated by the empty language, which of course is the empty language itself. Remember last day I told you the definition of concatenation. Remember, I take pairs of strings from one. So I take pairs. I take one from one set and one from the other set. I do this for all combinations of the strings in each respective language. That's what I do when I do concatenation. That's what the expression when I concatenate them is doing. So when I have something like this where I have no strings, and this has or may have strings in it, when I try to concatenate something with no strings with a set with strings, there's no way I can pair them, meaning that the set will result in an empty set, or the empty language. This is in contrast to this one right here, where I have a string. It's just the empty string, right? And has no symbol, so I can concatenate each one of the strings in L with the empty string, and I'll just end up with each of the strings respectively, because it's just a string with no symbols in it, right? That's the difference. So just know the difference between these two. So that's why we call this one the annihilator for concatenation, because it wipes out L. It's like the Terminator coming in. It's come to terminate you. And one other rule I want to point out is for union. So this is for union. So if I imagine I ask you to concatenate L with itself, sorry, not concatenate, let's perform union with itself, like L union L. This is just L. Why? Because remember, the expression L represents a language L that consists of a set of strings. If I take a set of strings and I union those with the same set of strings, I should end up with the same set of strings, right? That's what this is saying. Okay, so are we all good with these rules? I'm going to give you some more. These ones involve, the next ones are going to involve star. So below are more with star or closure, whatever you would like to call it. This says closure. The U kind of got crushed in between the S and the R. That's pretty epic. So the first one I want to point out is, and you might ask yourself, Dan, what happens when I have a star operator and then I apply a star on top of that star? So I want to address this. So if I give you L, I apply the star operator to it. Then I have another star out here. This is actually equal to L star. You might ask, Dan, how the heck does that even work? So let me explain this. So if I have so remember what the star operator says. I could take none of the strings of L. I can take one of each, two of each, three of each, so on and so on and so on. But that's going to result in, so if I do this with this side, that's essentially what we're talking about. On this side, I could do that. But you'll notice that after this process, because remember, this is going to end up being a language that has an infinite number of strings in it, right? With only rare exceptions. So when I do this, if I apply star to that, then I just pick from those strings again and again, and I end up with the exact same set. So if you're wondering, when you take a star and then you have a star again, it's just, they essentially are just going to morph into one star. So I just want to point that out. So if you see I have a star and then you have another star, it just contracts into a single star. Because I'm just taking 0, 1, 2, 3, all the up to many times as I need. And then all the extra stars telling me is I could take 0, 1, 2, 3 of these things. But those things are already things I already have exhausted. So it's not going to be any different. So one that I should point out that I have not addressed for you is what the heck, the empty language, so the expression for the empty language when I apply the star operator to it. This is going to be one of those funny examples. So this is, believe it or not, epsilon. If you think about it, the definition, it actually comes from the definition of star. You might ask, Dan, well, why? Okay, remember, I can take none of the empty set. I could take one of it, I could take two of it, I could take three of it, but it's more of a technicality because when I take none of it is this. So it's a technicality why this actually is true. Quite similarly, if I have the empty string, well, the expression for the empty string, so remember, this is a set containing the empty string, and I apply the star, I end up with just epsilon itself. So the star just doesn't do anything. Remember, I just keep giving you empty strings, right? So if I don't give you any empty strings, it's the empty string. The expression for the empty string. When I take 1, it's just the empty string. When I have 2 in a row, it's just the empty string. At 3, it's the empty string. 4, and so on. That's why. Another one, this is one I actually did use the last day. And this is a very useful one. So if I have the expression for the empty string, and I union it with L, which is an expression for some language, and I take the star of that, this is no different than me writing L star. So notice that because of the fact that I can choose to take none of epsilon or L, that's of course going to end up being no selections, which corresponds to the epsilon, right? So that means that if I have epsilon or this, notice that if I take none of them, the epsilon is still there, right? This choice of the epsilon is kind of superficial. So it makes no difference, because if I take 1 L or 2 L's or 3 L's, notice that I can still do this with L star, right? So adding this option is not really getting me anything unique. Does everybody see that? So this is how you can contract those epsilon choices. Okay. So that being said, that's all I have to say about the stars. I do have one remark, and this actually came up the other lecture. I wanted to point this out. Somebody had pointed this out the other day. I want to just feel like I want to remark about this. We can define, if I give you an expression L, I can write L plus 2b. So this is the modification of the star operator to be L, or L concatenated with L, or L concatenated with L concatenated with L, like this, and I can keep going. And you could think of this as 1 or more when we use it. So in star we have 0 or more, right, for our choices. Here this forces 1 or more. That's what this plus is going to represent. So you can use this as a shorthand, where it actually means, has the following property. So like L with the plus is equal to L star. So L concatenated with L star, which is of course going to be equal to L star concatenated with L. And if you're wondering the easy way to remember what L plus is, this is why I don't really focus too much on it, is because I could do everything with L star anyways. L star is actually exactly equal to L plus, where I union it with the expression for epsilon. Does everybody understand the second one? So L star is actually equal to L plus union the expression for epsilon here, the empty string. Does everybody see how this would be true? So this is another way I can actually just define what I just said right here. So remember, L star is where I take none of them, so none of the strings. So of course that resolves down to the set containing epsilon, right? So just, and then you just have everything else right here. So that's why you can define actually L star in terms of L plus using this right here. So that's all I really have to say about these properties. It's actually kind of neat that there's actually a nice algebra that you can use to express these regular expressions and simplify them down. Aren't these kind of nice? So these are kind of nice. So are we all good with this? Give me a thumbs up. Give me a thumbs up. I want to make sure we're all good. Hey, I see thumbs up. Awesome. Yes? Number 7. Number 7, this one? Oh, perfect. Okay. So this one, so if you want, I can actually break it out in the definition. So if I have the expression for the empty language, this is just literally the empty language, which, if it helps a little bit, it's just a set containing nothing. And what I'm doing is I'm using a concatenation operation with some language that's represented by that expression. So I'm concatenating it with, so I'm concatenating this with some language, and it has some strings in here. Now, the way I defined concatenation for you was that I take a string, one from, so if I call this, say, if I call the empty language A, and I call this other one B, I take a string from A, and I take a string from B, and I concatenate them. And the result of taking all pairs of these is the result of the concatenation operation for the two languages. So if I have, say, A, and this is, say, A, the empty language, and it has no strings in it. So it means I can't, there is no strings in here. I may have strings in here. So my language that I'm supposed to get as a result of doing this is supposed to be where I take each one of these, pair it with one of those, and that's how I do the concatenation, right? But if I have none in A, there are no strings in A, that means that there is no way I can pair an X with a Y such that I get this result right here. So if there are none, you can think of it like an empty list, and that empty list has nothing that I can pair it with, meaning that the result of this operation means that there's no strings, because I can't concatenate no strings with some strings. So that's why I can, when I do a concatenation with the expression representing the empty language, with any language, well, in our case, regular languages, this is fine, then it's no different than if I did it the other way. But it's either way, it's the expression for the empty language, which of course represents the set that is the empty language. So that's why it's called the annihilator, is that because there's no way you can pair the empty language with any one over here, because I pluck out each of the strings. So I take one out, I call this X, I call this Y, but in the empty language there is no X, so I can't pair them. Yeah, so there is nothing to be added when I have an empty, because I have an empty language, right? So that's how I build the language as a result of the concatenation, is I take one from each language and I pair them like this. But if I have none in this one, but I have some in this one, I can't pair them because there's none in here. There's nothing I can do to concatenate with. There's nothing to concatenate over here. Does that clarify that? Yeah, no worries. Yeah, no, this rule is a little tricky. At first, it's like, well, like, how do you get rid of the language? It's all about this technicality about how concatenation works. If you think of it more as a process where I take each pair of the strings, then it makes a lot more sense. Wonderful, wonderful. So, explain number 2 about empty set. Number 2 about, this one. Okay, so let's think about this. So this expression represents the following. So remember at some point I talked about, like, if I give you a language L and I raise it to some N, then I told you, okay, well, it's L0, then I take it and I union it with L1, then I do union with L2, and so on. And what I do is I take a certain number of symbols from that language. So now remember, L star is just where I take this and I keep going on forever like this. So if I have, say, L1, and imagine I have a language like this. This goes back to when we were talking about regular operators, right? So if you remember, if I take no symbols from a language, this is any language, then this surely is going to represent epsilon here. So it's a set containing epsilon. This would contain something, but remember, this is the empty language. Now, it's sort of a technicality out of the definition of L star. That it ends up that epsilon is sitting in one of these sets. And when I do the union of all of these, all I'm left with is epsilon. It's a very technical thing. But I recommend, if you really aren't sure about that one, just look at what the definition of L star is as a regular operator. If not, just go back to an earlier lecture when I talk about L, like the regular operator for star, and just expand out what that means. I think I had talked a little bit about L0 in that case there. And that's literally where this epsilon comes from. Is that all of this, everything but but this is relevant. But yeah, I'll let you, hopefully that addresses that concern about the this property here. But yeah, if you're not sure, just go back to when we talked about the regular operators. I think I talked a bit about this, what it means for L raised to a 0. Yeah, no worries. But yeah, like I said, some of these seem like really interesting because of that they all just derive from definitions. They're not sometimes very intuitive at first, but it's really just remember what the definition is. That's all it is. Okay, so now I want to talk a bit more about properties of regular languages. So some of these have been things that you've actually been playing around with a little bit, like for example on assignment 1. So I'm going to address some of these things right now. So, the proofs I'm going to keep in the notes. So if you're wondering about, oh, well, Dan, you didn't really prove that for me, or you didn't give me like a sketch of how you do it, it will be in the notes. Some of these I'll show you, some I'll leave in the notes, okay? So the first one I want to point out to you is that any finite language is regular. Any finite language is regular. That's the first thing I want to point out to you. And I want you to think about this while I grab another marker. Think about it in terms of a regular expression. So I want to just give you a quick gist of why this would be the case. So think about it. So here's sort of the idea behind this. So you would agree with me that if it's finite, then I can list out all of the strings in that language. I can call them like say I'll call it x1, x2, so on, so on, so on. And I could call it like xn and say there's n strings in my language. So this is my language. I'm just exhausting all the strings out for you. What can I do with this? What can I do with this to write a regular, like how do I justify that this is actually a regular language? Can somebody tell me? Yes, exactly. That's exactly it. Perfect. So notice all I have to do is I just take it and okay, well, x1, union x2, union x3. I can take each one of these and I can take all of them. But what I do is I take, because you'd agree with me that each one of these is formed from some alphabet, where it's a combination or a sequence of symbols from that alphabet. And you'd agree with me that all I have to do is take concatenations of all those symbols, right? And I get each one of the strings. I could do that for each one of my strings, and I end up with a regular expression. And you agree with me that if I don't like a regular expression, I can always convert this regular expression to any finite automaton I would like. And so that's the general idea. So if you give me any finite language, I can tell you it's regular. Is that kind of neat? So that means that any kind of really weird stuff going on with languages is not going to be finite. But obviously, if you're thinking about really big languages, you can see how this process would be very, very, very time-consuming if you actually tried to do it yourself. But does the general gist of this make sense to everybody? It's really kind of cute if you think about it. It's like, oh, well, look, there's all my strings. I can write a regular expression for all of it. So, like I said, you can always, I should point out, and I want to remind you of this, that regular languages are closed on all regular operators. So your union, or you want to write it like that, it could be your concatenation, or your star. Like all of these, if you give me a regular language and you apply a regular operator to it, or take two regular languages and you apply one of these operators to it, it still remains regular. That's what it means for it to be closed on a regular expression, or sorry, regular operator. Getting ahead of myself. So this is one very important thing to point out. So if you can write me, for example, any one of, say, those, so when I talked about like union, concatenation, star, and I told you at some point I was going to defer their proofs to you. Believe it or not, at this stage, because of all the stuff we've done up to this point, their proofs are ridiculously simple. Think about it. If I wanted to tell you how L1, so if I give you two regular languages, and I can, because of their regular languages, they do exist, of course, regular expressions for them by Kleini's theorem. So if I wanted to take the union of two regular expressions, you would agree with me that that should stay a regular language, the result of this. So that's what the expression is going to describe. It's still a regular language, right? So the way you could prove the closure on any one of these properties is you do basically this. You take, okay, well, each one of these has an operator as a regular expression. We have ways of describing regular languages using regular expressions. Remember, I use a capital symbol, right? Like I go like L or F or something. And I could describe that as a regular, like as a regular expression, right? The result of this. But what does that mean? Well, I can convert this to a finite automaton of my choice, which if ever I needed one such thing, it exists. That's all you need to know. And guess what? There's the closure property right there. So it spits right out of all the stuff we've done up to this point. That's actually how you could verify any one of these proofs. But there are other ways of doing this. You can manually create DFAs, for example, to prove some of these properties. But as I'm going to mention, there are some clever ways of doing this using regular expressions and also epsilon NFA. So I'm not going to talk about union, concatenation, or star, because essentially all you have to do is you just build a regular expression and hey, look, by Kleini's theorem, there's a way I can go and convert it to something else that by definition is regular, right? Is that kind of neat? It's very slick, isn't it? That it's all built right into the theory. It's almost like it's by design. It actually was. It was by design. So I want to talk about some more. So there are more. Given regular languages L1 and L2, I'm going to talk about various different operators and different things you can do with languages, and we're going to talk about them being closed. So the first one is complement. So if I give you some language L, say if it's L1, I could say L1, the complement of L1 is regular. So if you don't recall, remember, if you're working on assignment 1, the proof for this is actually what you're doing right now on the assignment. So I gave you actually the main step in this proof is that I gave you some DFA where you could switch around the final states with the non-final states. If you do this, there is actually a way you can build me a DFA that accepts the complement of a regular language. So if you're wondering how you prove this, that's actually what you're doing right now on the assignment. So you can just derive this using definitions about the two DFAs. So you don't need anything too fancy-pantsy for this one, but you'll see that it's a little bit fun. It's kind of fun. It's all built by construction. So this is an example where you could literally build me a DFA. Yeah. So if you're wondering, but I'm expecting you to remember just write out what it means for each of the DFAs, and then you just simply try to connect them, try to figure out what the relationship is between the two DFAs. Break it into two cases even, because remember, a DFA either accepts a string or rejects a string, and it always stays in one state, right? So complement, that's complement there. Intersection, this one's also another one I mentioned for the grad students, but I didn't require you to prove it or anything. So this is, say, if I give you intersection, so if L1 intersects L2, this is regular. And if you want to prove this, use De Morgan's law. So if you remember De Morgan's law from set theory, you use De Morgan's law to prove this, because you already know that union is closed, right? And you also know that complement is closed. You can rewrite intersections in terms of unions and complements. I'll have the proof in the notes. So you might ask, okay, well, what other things can you do? Another one is set difference. So this one's closely related to complement. So what I'm saying is if I give you L1 and I do set minus, some people write literally a minus, that's okay. I'm not too picky about these things. L1 set minus L2 is regular. So if you're wondering how to prove this one, believe it or not, because you have intersection at your own disposal, you can actually rewrite set difference in terms of intersection. So if you have this one, then you could prove this one really easily. It's actually like a 2-sentence proof. Like it's like it would almost insult your intelligence if I wrote it here on the board. If you're familiar with your set theory. So I'll put it in the notes. Like I said, it's like 2 sentences. It would hurt me to write it. I'll just remind you that if I write, I'll just write just mainly the idea. So if I have L1, L2 like this, notice that this is just L1 intersect L2 complement. So once you see that L1 set minus L2 equals L1 intersect the complement of L2, you'll see quite quickly, okay, well, look, this is intersection, that's complement, so you, okay, well, L2 is closed like there, and there's intersection right there, right? So you just invoke each one of these successively to build the statement. And say, oh, look, that was regular, so when I take the complement, it has to be regular. When it's intersect, okay, well, intersection, well, okay, that's closed on, that's regular. So the result of all of this has to be regular, but that's equal to L1 set minus L2. Now, the one that I want to talk about is, actually, let's do it on the next board here. Let's go back to the other board. I want to do this one with you because we haven't talked at all about reversal. This one, I want to give you the idea of how you can prove this one. It's actually kind of cute. I like it. Okay. So I got to define reversal for you, because we haven't talked about reversal up to this point yet. It's going to be relevant more as this course progresses. The reversal of a string, W, where I have symbols A1, A2, A3, all the way up to an minus 1, an, is the string written backwards. Like I said, is the string written backwards. Is the string written backwards. Like I said, it's kind of cute. Backwards. So if you really need me to write it out, it is an minus 1, all the way down to a2, a1. So it's just, you take the string, you flip it like this. So everything that started at the beginning is now on the end. Everything is at the end is at the beginning. You flip it, just like this. Hence reversal. It sounds like some sort of name you would give a roll in like a game like Uno or something. Reversal. So I'm going to denote, let's call, I'm going to denote the reverse of a string, W, as W with a capital R as a superscript. So if I write WR like that, that means it's the reverse of W. And the reverse of language L as L with the capital R as a superscript. So what I'm going to do is I'm going to show you a rough idea of how you prove that if L is regular, then the reverse of L is regular. Now, just to be clear, LR, like this, the reverse of language L, that is just simply where I take all the strings and I reverse them inside that language. Just to be clear. So I'm going to say if L is regular, so is LR. So now there's a couple different ways you can prove this one. I'm going to give you kind of like what I consider kind of like the coolest way of doing this. And it really is intuitive with the concept of reversal. Is I'm going to give you a sketch for how you do this. Here's a sketch. So watch this, watch this. So if L is regular, then there is an epsilon NFA M that recognizes L. So what I'm going to do is I'm going to construct a new epsilon NFA from this one. And you might ask, Dan, why do we use these epsilon NFAs and whatnot? Well, I told you it was about design. Like, it made things much more expressive. This also applies with proofs too, because the epsilon NFA gives you more flexibility to make all sorts of weird transformations that you might at first say, hey, like, I can't do that with a DFA, but sometimes you can do these things with an epsilon NFA. So I'm going to construct a new epsilon NFA M prime that recognizes LR as follows. Now, I have a question for everybody. Would you prefer if I drew you a fun picture or write it out? Because I'm not going to be testing you on like writing it out formally here. I just want you to just see the idea. Picture. I'm going picture. Survey says picture. So watch this. So imagine I have M, and so this is going to be what M is going to look like. So this is M, and stuff happens. So here's the start state of M, and there may be stuff that happens in here. There's a bunch of stuff that happens. And in here, there might be final states. There might be a bunch of final states kicking around. There may be more of them. I don't know, but they're all in M. It's like all of this is M. So there's a whole bunch of these. So that's what M looks like. What I'm going to do, this is how I'm going to build M prime. So first, everybody understand that picture. So that's so I have a start state. This is all in M. I should be clear. This is M. It has a start state and there's some final states. I don't know how many there are. And now all I'm going to do is watch this. Watch this. So imagine I have transitions that go, say, this way towards the final states. Here's how I'm going to build M prime. So M prime is going to work like this. I'm going to have my final states just like I had before. All the states are going to be almost exactly the same. I'm going to have my start state over here. And I told you I had a bunch of transitions that go that way. I'm just going to reverse all of the transitions. So all the transitions that I have in M prime, they're going to be the reverse of the ones I have in M. So I'm going to reverse all the arcs. So I'm going to reverse all the arcs. So now this is M prime right now. I'm going to do one small thing. So notice that I still have this idea that, okay, well, that was the start state, right? These are all my final states. But do you see where I'm going with this? I'm going to just literally take M and I'm going to flip everything. So now instead of it being where now there's a start state and I go towards the final states, possibly, what's going to happen is I'm going to start at something that's going to get me to these final states, and I'm going to work towards the start state. So now these will no longer be final states. So these are not final states anymore. These are not final states anymore. This is now, the old start state is now the new final state. So now the start state, so the start state is final. So this is the only final state. It's the start state. And now these are not final states anymore, but now I need a start state. So now remember, this is an epsilon NFA. So I'm going to create a new state that's going to be my new start state. So this is my new start state. And I'm going to put transitions towards all of the old final states. So these are my old final states. These are my old final states. I put transitions from the start state to the old final states. What should I put on these transitions? Epsilon. Perfect. That's why I like having the epsilon NFA. I can do very slick, simple things like this. So now look how, isn't this really nice and intuitive if you think about it? I want the reverse of all the strings that get accepted, right? For the language. In the old one, they went this way, right? All I did is I just simply reversed all the transitions, and then I introduced a new start state. Now these final states aren't final anymore. The start state is. And I just feed from this start state to the final states, and all the transitions are in reverse. So the idea is very simple. So you just like reverse all transitions. Transitions. And then you add, I apologize, it looks like it's kind of melting. Add new start state with epsilon moves. That's just the idea. So I just go from this new start state to the old final states, and I just feed it through the other direction. Does everybody understand the idea? So all I'm doing is I'm just like when I took the reverse thing and I just went whoop, like this, I do the exact same thing to the epsilon NFA. Is that kind of neat? But yeah, this is just to give you an idea of how you can actually try proving this if you wanted to try proving it. It's actually, like, this is why I wanted to show you some examples. Like, some of these are just straight out of regular expressions. Some use a DFA, like the example on the assignment. The other ones are like these, where it's like, okay, I can use epsilon NFA. Because of the expressive power of an epsilon NFA, I can build easily new epsilon NFA that accept the language of desire, like my desired language. In this case, it's the reverse. Okay, are we all good with this? Give me a thumbs up. I just want to make sure everybody's all right with this. I know my picture looks like it melted. It's like really old cheese in a microwave. That's kind of a visual image. But everybody understand the idea? I think we're good. I think we're good. So I want to talk briefly about a couple of other things. I'm going to put more remarks about this in the notes. So if you want to give it a read, I recommend giving it a read. Because there are decision properties that regular languages do have. And you remember I talked near the beginning of this class about decision problems, right? I talked about, like we talked about membership. We'd asked, how do I know if a string is in the language or not? I want to talk briefly about case problems like this. So I'll say we are often interested in certain decision properties or problems. We'll say decision problems. So some of these are going to come up as we progress through the course. Some are going to be harder than others. So just be aware of that fact. So sometimes if you ask me, can you do this with this language? It may not be a very easy question for me to answer off the fly. So, like I said at the beginning of this course, how it's kind of like a programming class in some weird way, where it's like you can ask me if I can do a thing. It would require me some time to really prep and check it for you. But the first one I want to do is talk about testing emptiness. So the question is L empty? So is the language L empty? So now you might ask, Dan, why is this interesting? Because remember, if I just gave you L, you can easily look at it and say, hey, look, that's empty or not, right? But that's not really what I'm asking. I'm asking, given some representation of L, is it empty or not? So can we test if L is empty for some representation of L? And the answer is, of course, yes, with the regular languages. So I'll describe you one way. I'm going to put a little bit more, actually, I'll let you take a look at it in the notes, but I'm going to give you a brief summary of the idea. So if I give you a finite automaton, so remember, what does it mean in a finite automaton for a string to get accepted? We process a string W. From the start state, we move to a final state. And upon finishing processing, we're still in a final state, right? That's what it means. So I start at some start state. So I'm at some start state. And I do some stuff in here. I process W. So I process some string. And it gets me somewhere to a final state when I'm done. So this would be the process if W is accepted by a DFA, for example. That's what would happen, right? That's what it means to get accepted. So you would agree with me that if such a W existed, that means that the language isn't empty, right? Because it has to accept at least one string. So testing emptiness is testing whether a final state is reachable. A final state is reachable from the start state. So this is actually a graph reachability problem. So notice that in this process, I need to find a directed path or a set of transitions in our language for the finite automaton that take me from the start state to the final state, right? There just has to exist some path that gets me there. So believe it or not, all you really need to do this is a graph traversal algorithm. Does everybody see that? So all I need is just one way I can get me from start state to the final state. And that's how I know if it's empty or not. So this is an example of a reachability problem. So this is a reachability problem. And in the notes, I give you a description for how you do this, and it effectively boils down to whether you want to interpret it as depth first search or breadth first search. So if you find one path that takes me from a start state to a final state, you know it's not empty, right? So if this path exists, L is not empty. That's what this says. L is not empty if there's a path that takes me from the start state to a final state. Why? Because remember, all of those arcs, if you think of it like a graph, correspond to my transitions, which I read symbols. And there's very efficient algorithms for doing this. So there's very good algorithms for this. That's the big thing I really want you to know, because this takes there's nice linear time algorithms for doing this kind of stuff. Now, if I give you a regular expression, or let me write it like this instead. A regular expression. If I give you one of these, what can I do? I can always convert it to an epsilon NFA, then do this process, right? So that's one way you could do this. There's other ways you can test with directly expecting, but you'll find that this algorithm works pretty darn good. But there are ways you can check these directly, but I'm just showing you that there exists a way to do it. But are there any questions about this? If there aren't, we're going to stop right here because it's time. When we come back, I'll show you that there exists an algorithm that you could use to test the equivalence between two regular languages. It's not going to be a constructive proof. There is a way to get a constructive proof, but since this is more of a theory of computation class more broadly, as opposed to just a automata theory class, I won't have time to talk about it. If I had another month, I would teach it to you. It's really neat. But when we come back, we'll do that, and I'm going to show you how we can look at non-regular languages. So that being said, I want to say thank you very much, and have yourself a beautiful day. See you later.